All right.
Okay, take it away, Michelle.
All right. Well, good morning, everybody. My name is Michelle Crepeau, and I'm the museum conservator for the North Carolina Maritime Museum Systems. And thank you very much for joining me on this kind of gloomy Thursday morning to learn a little bit about acid-base chemistry and how it affects archaeological conservation and how we use it in archaeological conservation to sort of correct some of the problems that are exhibited with these artifacts once they've been excavated. So just to give a brief, my cursor is not. We'll be having difficulties. One moment, sorry. Oh no. Okay, there we go. Sorry, my computer was having a moment, but just to give you a brief overview of today's lecture, we're going to go over a little bit about what makes an acid and a base, sort of what the various definitions are, so you kind of understand a little bit of the background. We're going to talk a little bit about how acids and bases impact different types of materials that we find on an archaeological site. So that means inorganic materials as well as organic materials and composites, and how they kind of affect their state of preservation. So some of these artifacts, explains why they are the way they are when we retrieve them. We're also going to talk a little bit about where the various places archaeological materials come into contact with acids and bases, both sort of in that initial burial environment as well as post-excavation. So where do they come into contact with acids and bases in the museum itself? And then we're also going to talk about how conservators try to address those problems presented by contact with acids and bases that affect these artifacts and affect their preservation long-term and immediately. To kind of get right into it, there are a lot of different ways you can describe what an acid is versus what a base is. I think when you think of an acid or a base, you really think of an acidic or a basic solution. So basically something that is then dissolved into something else, essentially, that then becomes acidic or basic. So we think of an acid solution, we think of a basic solution. Generally, we're talking about water. Water is sort of the universal solvent. So one of the definitions for an acid or base is anything that is added to a solvent like water that it basically changes its chemical properties. And specifically what it is doing is that an acid, when added to a solvent, will increase what the hydrogen content. So basically it increases the number of protons or numbers of hydrogen ions in your solution. A base will do something very similar, except instead of hydrogen ions, you are getting hydroxyl ions. And the shorthand will continue through the duration of the presentation. So anything that's sort of marked in red will denote an acid. Anything that's marked in blue will denote a base. And then sort of the real takeaway is that hydrogen is shorthand for an acid, and hydroxyl, these little OH negative symbols, are shorthand for your base. So this is sort of the most common idea of what a solution is. And just sort of a fun fact, but water, our universal solvent, can be both. It's why it's such a good base for all kinds of chemistry, and sort of helps really support why life is the way it is on this planet. Just because water can exist as both a hydrogen ion as well as hydroxyl ion, as well as a hydronium ion, which is that kind of weird little guy in the corner over here with the 3 hydrogen atoms attached to the oxygen. Hydronium, for all intensive purposes, also functions like a hydrogen ion as well. So it also denotes an acid. And these can exist basically simultaneously in the world at the same time. And this is called, and basically a material that can act as both an acid and base is known as amphoteric. So that's kind of just a fun little vocabulary word for you to remember. Amphoteric means that it can act as both an acid or a base, water being the most prevalent one here on planet Earth. And this is probably kind of how, when you think of acids and bases in your everyday life, you think of pH. What pH is a measure of hydrogen activity in a given solution. So basically what that means is it's an indirect way of measuring how many hydrogen ions are in a solution at any given time. And the more ions you have, weirdly enough, sort of the lower you rank on a pH scale is because it's an inverse inverse scale, or essentially that means the lower the number is, the actual greater the acidity of your material is, the more hydrogen content exists. Conversely, on the opposite end of the scale over here in our sort of base end, this means that kind of an inference that the less hydrogen there is, that means the more hydroxy there is in a given solution. So it's also sort of an indirect measure of hydroxy content as well. So this end of the spectrum with sort of your drain cleaner, your bleach, you have very little hydrogen ion content, much more hydroxy ion content. We're right here in sort of battery acid land, that is very, very high hydrogen content. And then right here in neutral zone, that means that there's roughly equal amounts of hydrogen and hydroxy in a solution at a given time. They balance each other out, they neutralize each other, hence the term neutral. And you can see that even things that we think of as being very neutral, mostly because they're in our body when we ingest them, actually do have a slight acidity or baseline alkalinity to them. Milk, for instance, is slightly acidic. Your blood is slightly alkaline. And these are just sort of kind of giving you an idea of the actual acidic or basic content, sort of what are the actual chemical molecules that are contributing those hydroxy or hydrogen ions at a given point. So you can see everything from sulfuric acid all the way to potassium hydroxide on the scale. And of course, not all acids and bases, other types of definitions of what makes an acid or a base, when you kind of get more into the chemistry, you're also looking much more of what these molecules are actually doing, not just that they are sort of qualitatively being dissolved into a solution and sort of changing how many, just the pure number of hydrogen and hydroxyl ions, but also sort of how they're interacting with each other. So another way to kind of think of an acid or a base is something called protonation. And it's basically, an acid is anything that is capable of exchanging a hydroxy ion. So it's able to donate a hydroxy ion, a hydrogen ion to another molecule. So basically, it's essentially giving the hydrogen to something else is kind of how we define one definition of an acid. A base is then receiving that hydrogen ion. And this is kind of, and it makes a conjugate acid and a conjugate base. And you can think of these as almost a mirror image of the base and the acid that you're starting out with. They will always produce sort of a mirror inverse image of themselves. Well, your base will produce a conjugate acid, your acid will produce a conjugate base. This will be important later on in the discussion, since these kind of influence some of our conservation treatments, but just know that a conjugate acid and a conjugate base are something that exists. When you dissolve, in this case, nitric acid into a solution of water, you'll produce hydronium ions, which is your conjugate acid, and nitrate ions, which are your conjugate base, that are existing in this milieu of solution. You can also, of course, not everything has to be water-based or even solution liquid to liquid. This is an example of two gases. Another thing about this type of ion exchange is that you also tend to make things with it. This is an example of an acid and a base combining to make something that you might recognize as a salt. So like another definition of acid and bases are that they are two substances that when combined produce a salt, that you might recognize that. And sort of the last definition is very specific. It's also looking at not just hydrogen atoms being exchanged between molecules, it's also looking at electrons. Electrons in sort of the world of our subatomic particles are the negatively charged particles that sort of surround your atom, your nucleus. And they're also basically what allows different types of elements to bond together, what forms atomic bonds. So this is really about bonding. This is looking at acid and bases in terms of bonding, where basically the takeaway from here is that an acid is something that is very good at stealing electrons from other types of, from your base, from your electron donor, from other types of elements. In this case, hydrogen is a very, very good stealer of electrons, and we'll see that play out later on. But this is all about sort of where the electrons are going from one type of material to the next. And if this sounds kind of familiar, it sounds kind of like something we call our oxidation reduction or redox reaction. That's because it is. And again, it's just sort of context whether or not we call the participants in these reactions reductants versus oxidants, or if we call them acid bases, or if we call their products salts or not. But essentially, it's just sort of different names for the same types of chemistry that is all just very context driven. And generally speaking, we're really concerned about this type of definition in the context when we talk about basically metal types of metal corrosion. So like corrosion chemistry, which we'll get into a little bit later, but this is just sort of to pave the way for that. So now we're going to talk a little bit about the different types of reactions that acids and bases participate in, like the type of chemistry they actually do. So chemistry, this type of chemistry can both make things and break things. So an example of the types of reactions in which acids and bases are making things is what is known as the neutralization reaction. And that is when you have an acid and a base that are combined together and they make a salt, they make a new type of material. And generally, so that's what that illustrates. And there are different types of reactions. We call them sort of the series of completeness. A complete reaction is, you can think of it as a dance almost, where you have your acid show up, your base show up. They're looking for partners to match up their hydrogen ions versus the hydroxyl ions. And in a complete reaction, each one of those finds a partner. So they're perfectly matched up. Basically, they're all consumed in that reaction. And you get what we call a neutral salt. Probably you know this one, it's sodium chloride, table salt, sea salt. It's one of the more common salts. And it has a pH neutral that indicates that it has an equal amount of hydrogen and hydroxy ions that went into the process of making it essentially. There's nothing left over. In contrast, you also have partial reactions where you have an unequal number of hydrogen and hydroxy ions that showed up to the party. So not everyone's going to get a partner. So what happens is you have these sort of excess hydroxyl ions and hydrogen ions that end up sticking around in that completed salt, essentially. They contain hydrogen and hydroxyl ions that when you then put them into solution, for example, they have basically extra hydrogen and hydroxy ions to donate to that solution, which we discussed previously, means that they kind of influence the pH or the amount of hydrogen and hydroxyl ions in that solution. And they either increase or decrease that based on what they are. So if you have acid left over, if you sodium bisulfate, for example, if you put that in water, there's leftover hydrogen ions that will then go into solution and decrease or make that solution more acidic. And sodium bicarbonate is a really well-known basic salt that if you put it in a solution of water, for instance, it has excess hydroxy ions that will then change and raise the pH of that solution, making it more basic. So that's various ways in how salt chemistry and acid-base chemistry can make things. And these will be very useful to remember. We'll come back to these and see these actually sort of used in sort of real life examples in a little bit. And then we also have acids and base breaking things. These are sometimes called catalyzation reactions. There's two major ones I'm going to talk about. I'm going to talk about, first kind of give you an overview of the reaction itself, and then talk about them as they apply to specific types of materials, which we might find in the archaeological burial record. The first one is hydrolysis. Hydrolysis literally translates to water breaking. So it is essentially using water as a stand-in for both an acid and a base to break bonds between molecules or atoms. So this is an example of essentially you have your molecule, it has a set structure, it has a set overall charge, negative, positive, neutral. And what happens is you add water, for instance, or you add sources of hydroxyl or hydrogen, and then almost to this atmosphere, and they want to get in on this. They want to like kind of combine with these molecules that already exist. So what they do is they just kind of add themselves to the mix. They literally just attach themselves to part of your molecule, but the molecule doesn't really like it. So it was nice and happy and stable, and all of a sudden it has a hydroxy ion or hydrogen ion hanging off it. And this changes a lot of things about the molecule. It changes its weight, it changes its structure, it can even change its charge. And so as a result, it breaks the molecule apart into things that are more stable. So that's why you end up getting basically two things out of one, if you are. Hydrolysis is very important when it comes to understanding how acids and bases affect organic material. So anything that comes from a living organism, that includes plant material as well as animal material. And to think that's because plant material and protein or animal material are the base kind of units of what sort of makes up all our tissues and what have you, are very, very long fibrous strands of smaller types of molecules that are all bonded together. So for plants, you have series of sugars that are all attached to each other that make these very long cellulose chains. and different types of animal proteins, collagen and keratin being two of the most well-known. You have different amino acids that combine to create peptide chains that then create large-scale proteins and then networks of proteins. And these all have a very specific type of organizational structure, and they're very complex and very large sort of chains that are really kind of give you the various tissues the properties that they have. So you can kind of imagine where changing those can change how those tissues react. And there's acid hydrolysis and alkaline hydrolysis that then essentially break these large superstructures into smaller pieces. So in acid hydrolysis, for instance, you'd be using an acid to break glucose chains in a cellulose fiber. And alkaline hydrolysis, you might be using an alkaline or a base to break your protein into smaller subcomponents and kind of basically destroy those superstructures. And what this can have as an effect on the actual artifact is that you're breaking apart these materials, literally at a kind of a molecular level. You are breaking them apart. You are causing these fibers then to kind of crack and tear and break apart. And this causes a lot of stress on the actual superstructure. And if you have enough stress introduced, either because you've changed, you have the same amount of space, but you've all of a sudden introduced smaller materials that are supposed to fill that bigger space. You have a lot of mechanical stress put in your artifact, so you get breakage and tearing of those fibers. Right over here is an example of a very common one that affects leather. This is not necessarily archaeological. This can also happen in a library. This happens a lot with a lot of leather-bound books. It's a condition called red rot. And it is effective acid hydrolysis, where essentially you have this acid attack that is breaking these collagen bonds in the leather into smaller and smaller pieces until you almost get like this red colored powder, hence the term red rot. A lot of people think it's bacterial or it's microbial because it kind of looks like an algae or a fungus or a mold that's growing on these books, and it's not. It's actually the book itself being digested and broken into small little tiny pieces that literally come off on your hand. So that's a very kind of common example of acid hydrolysis in action. In terms of the effects of hydrolysis, not just cracking and tearing of the individual fibers directly, there's also effects on the overall superstructure as well. There's a phenomenon called cross-linking, where essentially you're breaking, when you break the bonds between these individual glucose molecules or amino acids and peptides, those little bodies, those little pieces, they want to recombine. Like, they're not necessarily happy just being a solitary glucose. But what happens is they recombine in ways that are kind of weird. As cross-linking, as you can see right here, they literally start going from a straight row where they were kind of nicely aligned in a link to bonding basically across rows in ways that change the way that the overall material behaves. You can also get some types of materials like leather actually has a certain amount of cross-linking already. This sort of connection between different strands, like kind of unilateral connections, or actually have some good mechanical properties that lend strength when done in the right kind of way and combination. So when you have a situation like leather where you already have cross-linking, what happens is when those bonds break, including those cross-link bonds, you get the rebonding, but it happens all wrong. So you end up with this kind of weird jumble called recombination. And this is sort of what it then leads to: shrinkage and brittleness and basically just general loss of mechanical integrity of your material. This is a really good micrograph actually of collagen, so animal protein like you would find in sinew or rawhide kind of material. Right here is your normal collagen. So this is kind of what it looks like. You can see everything's in these nice flowing, well-organized strands. And then up here you have your disorganized collagen that has been affected by maybe hydrolysis reaction that has caused this breakage in this incorrect sort of recombination of elements, where you get this is kind of a jumble. And you can see, like, obviously it's tight, it doesn't stretch, it doesn't bend, it has no flexibility, which makes it very brittle and easy to break. So these are kind of various, if you think of this happening to the entire, if it's happening in one little spot, that's not so bad, but if it's affecting the entire leather object, for example, like the entirety of your book binding cover, for example, you can see where this would really affect and damage your artifact on a very large scale level. And the last one is an example of how these effects can also be sort of self-sustaining. Once you sort of have hydrolysis, it can be self-perpetuating. A really good example of this is with things made of wool. Wool, even though it's a fiber that we use in clothing a lot, is actually a protein. It's an animal product. It is made of amino acids. One of the amino acids that it actually has just inside of it is something called cysteine, which has sulfur. So it has elemental sulfur in its structure as part of those amino acids. It's also cross-linked as part of its normal structure. And then when you add moisture, for example, and all of a sudden an acid, and you do get sort of recombination effects when you have these cross-linked chains starting to break apart and then recombining in different ways. But you also have that sulfur that's part of that cysteine bond that is also basically being ripped out of the structure and sort of left to its own devices. And so it will start to combine with other things and form other types of materials, including sulfuric acid, in which case you get this sort of self-perpetuating cycle of acid attack that is then perpetuating more acid attack within itself. And actually, wool is so sort of prone to doing this that we often use it in something called an Audi test, which is basically a way to test how corrosive your environment is, or to artificially age materials that you're working with to try to get a sample. And basically all you need to do is wet it and put it in a jar with a piece of metal, and in a pretty short effect, you will start getting tarnishing and corrosion of that metal as the wool itself is breaking down and producing the sulfuric acid. So we kind of do use it for our own research purposes as well, but also why you don't see a lot of wool used in museum exhibits for this purpose as well. And then finally, kind of getting to our last sort of catalytic effect. This is more when we kind of talk about hydrolysis in the context of inorganic materials, we tend to talk about it as an electrochemical degradation. So we're going back to that definition of an acid base as an electron exchange between two materials, in which your acid is very electron hungry and likes to take electrons from other materials. So this is an example, as you have your hydrogen content free floating in your solution. They're sort of coming up to your zinc body right here, and they're like, I want that electron, I will take it. So they are taking electrons from the zinc. The zinc in turn is essentially, those electrons are what was holding the zinc together. The zinc ions are then like, well, there's nothing holding us together anymore, goodbye. So these are dissolving into solution at the same time. This is an example right here of zinc being put into an acidic solution. You can see right here in the middle, you have a lot of bubbles that are forming. Bubbles are a really good indicator in conservation, other types of chemistry, that the reaction is happening, something is happening, because this gas production, these bubbles, are a result of hydrogen accepting those electrons and becoming hydrogen gas. And then over here in the last one, you can see it's all nice and cloudy. That cloudiness is all that dissolved zinc metal that is now in solution. So you can sort of see this dissolution by way of electrochemical degradation of metal artifacts in action. And a lot of this has to do with the fact that inorganic materials, inorganic basically just means anything that does not have a component in it that was once part of a living organism. That includes metal, ceramics, things made of glass, even lithics. And what these basically are is that these are often very rigid, sometimes very crystalline structures of minerals, sometimes on a very large level, and with ceramics and lithics, where you have these very large sort of mineral components trapped together and kind of cemented together in a matrix. And then you have metals, which are much more sort of refined mineral contents, where you have this very distinctive grain structure. And then glass is amorphous, but basically the takeaway is that these are all sort of mineral-based materials that are held together in some form of structure. And what acids and bases do is they essentially disrupt that structure in their quest to get electrons from each other, essentially. Dissolution and etching is something you might be familiar with. This is probably one of the really most obvious forms of acid attack, especially on metals when it's happening at a very large scale. We often call it acid digesting, where you just have kind of very prolific, very large area of effects. We call it acid digestion. When it's very localized, it's etching. Sometimes we do this purposely. Sometimes it's just a byproduct of very small, very localized points of contact between an acid, like what's on your hands, and between an artifact. So this is a silver cup, and you can see it's covered in fingerprints. And these fingerprints are actually etched into the surface because your hands contain oils that will hydrolyze into acids that are then left on the surface of these artifacts. And if they are not wiped away or cleaned or rinsed, that acid will essentially dissolve the metal in those very localized spots and digest it, and leaving these whirl patterns from your fingers. So that is something that we often have to contend with all types of materials, not just archaeological things, but basically any artifact that's in the collection that can be affected by acids or bases. And that was kind of an example of a really one-to-one parallel, a really direct relationship between an acid or an acid or base and a substrate, some type of material. But acids and bases are also really important because it's not just this very direct sort of chemistry that occurs, but also kind of indirect, where acids and bases really kind of act as mediators. They help facilitate other types of reactions that are going on. The biggest one is probably the ability of certain materials to dissolve in water. Water is the universal solvent. It's the most prevalent type of solution that exists on Earth. And there's some materials that just don't really readily dissolve into water. Like, for instance, we don't really think of sand as readily dissolving into water, that silicate structure. Well, silica is a really big component of glass, including the glaze that you have on ceramic bodies. It's basically just glass. And that silica doesn't really dissolve in water. And this glass sort of structure is talking about these mineral matrices. It has a very particular mineral matrices that has different types of minerals that are kind of stuck in the silicate based super sort of netting, almost this matrix structure that is composed of silicon. And what acids and bases do, particularly in this case, alkaline hydrolysis, so this is a base acting, is that they help basically chop these large, very complex matrices into smaller, simpler types of materials that then become water soluble. So you can see, and then kind of introduce holes in the structure. And over time, your glass will actually dissolve because the hydrolysis has literally kind of taken this insoluble structure, punched enough holes into it, made it kind of a small enough, simple enough type of structure where it can actually be dissolved by water. And the same thing can happen with acids and bases. This is something you often see in lithics. We don't really think of things made of stone, for example, being really pervious to different types of degradation, including acids or bases, but that is close as incorrect. A really good example is what happens with feldspar, which is a component of a lot of sedimentary rocks, a lot of sort of limestones, et cetera. Feldspar is generally not itself very water soluble. What happens when you have an acid introduced into the environment, like through acid rain, for example, all of a sudden it gets broken down into more soluble components like carbonates. And so when you add moisture to it, when it rains, for example, these things are going to dissolve. They're going to open up the structure more so that you can get basically loss of your feldspar pretty deep into the material over time. And you can kind of see the difference over here between something that is very uneroded versus something that has been largely affected by acid. You can see sort of the loss of these feldspar components within the matrix of the stone. And this is usually a really big problem with a lot of monumental or outdoor type of structures. If you're a conservator who works with outside stone monuments, including like gravestones, a lot of this type of erosion that you see is a direct result of acids in the environment slowly sort of changing the chemistry of these materials enough that they can be basically just dissolved by the next rain shower. There's another type of material that affects glass in particular called ion exchange. This is an acid attack actually of glass and other type of glassy materials like glaze on ceramics. And what it is an exchange of alkali metals for hydrogen atoms. And when I mean alkali metals, I mean sort of in the periodic table sense. So things that fall in this row over here. And what happens is that you have hydrogen, so an acid in contact with the material that literally changes places with other types of minerals that are in the silicate structure. So these alkali metals that are part of the structure suddenly are gone. They're replaced by hydrogen. And you might have seen archaeological glass. You might have had questions about how it doesn't really look like glass anymore. And that's because of this alkali leaching, this acid attack, where you have color changes. So you can have an iridescence or an opacity that forms as a result of this. You can also have this weird kind of crust that forms on the sort of the top of the glass. That is also a form of this alkali leaching and a result of the very kind of real visual effects. And of course, over time, you can see over here that these alkali metal structures are leaving, and what's left is this very kind of open silicate silicon structure. And as we talked about previously, this more porous open structure leaves it a lot more vulnerable to then being attacked by hydroxy ions, so by your base alkali hydrolysis, which over time can then basically chop up the structure. And over time, you can have dissolution or loss of this glass over time, which is why you can also have like pitting in glass things and loss of layers over time. So we think of glass as being very kind of stable. We think of glass as being very impervious, much like stone, to a lot of environments, especially in the burial environment, but it actually is very sensitive to pH changes. And they often work together to sort of destroy these beautiful pieces, or at least change them in very, very dramatic ways at times. And then finally, we have our metal corrosion, our corrosion chemistry, which as we went through kind of previously, is those hungry hydrogens looking for electrons and taking them from our metal artifacts as a result, and sort of causing their dissolution. And what happens also is that pH plays a very big part also, not just in the dissolution of those materials, but also in what types of corrosion products form. These are often dictated by how much hydroxyl or how much hydrogen are in the environment, and can lead to different types of materials being formed. And those materials themselves can be more or less reactive and can continue to corrode, or else they can be very stable and almost protected for those artifacts. So this is something we'll get into a little bit later when we come to the types of things conservators do to try to mitigate the effects of acid spaces. But just remember that I said this, and this doesn't just affect actual metal artifacts too. It affects anything with metals in it. This also includes paint pigments. This includes glazes on pottery, for instance. Anything that has like copper or iron in it that was used to kind of maybe add a pigment or a color to something can corrode in this way as well. So it's not just iron or copper metal objects that undergo these processes and are affected in these ways. It's also components of other materials that kind of work together. And kind of on that note, we're going to talk for very, very briefly about composite materials. So these materials are materials that have organic parts and inorganic parts as well, and basically, and that includes like teeth, ivory, bone, antler, that kind of material. And really the takeaway from here is that they will deteriorate kind of preferentially based on if it's acidic or if it's basic, based on which material, if it's the organic part or the inorganic part, which is exposed in any given environment. All right, so where do these artifacts encounter acids or bases? Well, ultimately, of course, they initially encounter them as part of the burial environment, either in the water or in the soil. There's chemistry that is happening all around, and there are different types of soil chemistry and water chemistry that make slightly more acidic environments versus slightly more alkaline environments, which kind of cause that initial degradation, that initial hydrolysis, that initial dissolution, some of the initial corrosion that we're seeing. And try to give you kind of an example. A really good sort of comparison are two different types of sort of watery, half terrestrial, half waterlogged environments, the bog and the fen. And basically the really kind of big components are that acidic environments tend to be very stagnant. There's not a lot of water flowing. There's not a lot of flow of air or current that's kind of constantly replenishing the water. The water just kind of sits there, and as it sits there, it becomes more acidic. They also tend to be very mineral poor. So there's not as many dissolved minerals in that area that are kind of buffering that acid. Things like carbonates and calciums that can kind of help with that. As a result, there's very low pH and low oxygen. Whereas a fen, a lot of people are always asking me what the difference between a bog and a fen is. Well, a fen is a lot more dynamic. There's a lot more flowing of water. There's a lot more circulation that occurs. There's a lot more mineral enrichment as a result of that flow. There's all kinds of things being deposited in a lot more constantly that can help sort of buffer that environment. Though interestingly enough, acid environments, despite how much we've talked about acid hydrolysis in this presentation, is actually a really good environment for a lot of organic material, including bog bodies. That's why they're called bog bodies, not fen bodies, is that these environments end up being very good for the preservation of a lot of organic material. And I didn't understand this for a really long time, because like acid hydrolysis is such a strong destructive force when it comes to so many organic materials. But then I had it explained to me, well, it's not so much that the acid hydrolysis is happening, it's that what's not happening, which is bacteria. Acidic environments tend to be very hostile places for a lot of types of decomposers like bacteria, which would thrive more in a more oxygenated, more mineral rich, and sort of more current dynamic situation than in these very stagnant bogs. So we actually will get back to these guys in a little while. They do have a part to play in the post-excavation environment. But yes, that is the difference there. And then after artifacts are extracted or excavated from their burial environments, they can continue to be subjected to acid-base chemistry in storage, in the gallery, even in the conservation lab itself. And that's largely to do because once they're in a burial environment, they've been there maybe hundreds of years, they've reached a sort of equilibrium with that pH, with that amount of oxygen, with that amount of moisture. And then when you excavate them, you are suddenly changing that environment very drastically, what they are exposed to. So they are being exposed to different humidity levels, different oxygen levels, et cetera. And these can really kickstart a lot of different types of chemical reactions. So we'll be talking about the way that humidity and oxygen in particular affect burial environment products. So things that were left behind inside the artifacts as a result of them being in an acidic environment versus a basic environment, et cetera. We'll also talk about how museum housing, display, and various support elements also can be sources of acid-based chemistry. Also, atmospheric pollution is a big one, as well as our own conservation materials. The discipline of conservation has had to change quite a bit in the last 40 years as we've kind of understood more and more about the effects of our own materials can have on the things we're trying to conserve. So first, we'll talk a little bit about different types of burial environment products. One of the most aggravating and most common is soluble salts. So these are salts. These are products of acid and base reactions that are soluble in water, which also includes atmospheric moisture. And if something's been buried in an area that's very salty, that salt over time will make its way inside the artifact, sometimes in places you really don't want it to be, like underneath your glaze. So this is an example. There's a bunch of salts that have precipitated onto the surface of our artifact. What happens is that when the pH increases, so they basically dissolve back into atmospheric moisture. And then when that pH drops again, they will precipitate out of it. And if they precipitate out of it on bad places, like behind the painted glaze of the ceramic, for example, those painted sections basically can be physically forced off by that crystal growth. So you have this mechanical damage that is done by the growth of these crystals in unfortunate places in our artifacts that can actually break our artifacts apart or result in loss of very critical material. Soluble salts are also very critical when it comes to continued corrosion activity that occurs even post-excavation, because again, a lot of those acid-base materials from the initial corrosion processes that are happening in the burial environment, they're producing salts. For iron, one of the most aggravating salts it produces is ferrous chloride. Ferrous chloride is a salt that when then exposed, even at room temperatures, to atmospheric humidity, will basically go into solution, and then all of a sudden you have chloride ions hanging around. And if there's any hydrogen ions in the mix, which there are in water, you're going to very quickly get yourself some hydrochloric acid. And this hydrochloric acid will then start to digest your artifact, often in these little pockets that you see. And as these pockets grow, they become very kind of self-sustaining. They become that catalytic sort of self-sustaining acid production force. And to the part, you often get what we call corrosion blisters. And this happens as a result of that acid corrosion, where you have a pit that is formed because it's being dissolved by really concentrated, localized pinpoints of hydrochloric acid. It's also building almost kind of a blister or bubble around itself. So it's like trapping this chemistry inside. And when you pop these blisters, you end up with these rather ugly looking holes, these craters in your artifact from this chemistry that's occurring. So soluble salts are definitely a big problem. They cause a lot of both chemical and mechanical damage to the artifacts post-excavation. And sort of as an extension of this, even artifacts that aren't made of metal but have been in contact with metal, especially iron, can be subject to a lot of these sort of ferrous chloride, atmospheric moisture sort of feedback loop of hydrogen chloride production, just by virtue of having what we call metal migration or metal stainings. You literally have some of your corrosion product has literally physically moved on top or of another object and caused it to become impregnated with this iron or stains the surface of this iron. So that can, depending on what it is, you have this hydrochloric acid that's being formed. If it's an organic material, it can lead to, acid hydrolysis. And even if it's something like made of stone, you can sort of get that those solubility changes that acid helps facilitate and then the facilitated dissolution of parts of even your stone artifacts can go as well. And also going back to the microbes, which I mentioned earlier, is sulfur contamination. A lot of the microbes that exist in the burial environment don't actually need oxygen to survive. They are what are known as sulfur or sulfate reducing bacteria. They basically use sulfur components instead of oxygen in a lot of their respiratory action. As a result, they also put out sulfur byproducts, mostly hydrogen sulfate. As a result, this hydrogen sulfate can itself become trapped in the structure of, say, wood. It can get deposited into the cellular structure of the wood. Also, if there are any iron or metal components in your wood, for example, if it's part of a ship, if you have iron nails hammered in there, all of a sudden you have an iron and a sulfur that are in contact with each other, and you can get all kinds of interesting iron sulfur sulfides and iron sulfate salts as a result. And what happens, as you can imagine, once these are excavated, once they're dried out, even after they've been treated, we can still have problems with moisture problems that then induce sort of a sulfuric acid feedback loop. This is a big problem with certain really large scale, really well-known shipwrecks that have been excavated. If anyone's heard of the Vasa is a really well-known, beautifully preserved ship that sank in a river, was buried under all kinds of mud and boggy stuff, so not a lot of oxygen. The wood survived really well over time. However, the sulfate reducing bacteria impregnated it with a lot of sulfur and iron sulfites as a result. And it is to this day having sulfuric acid problems kind of into perpetuity as a result of that contamination. This can also happen to things in collections you wouldn't expect. One of the biggest problems in geological collections and fossil collections is something known as pyrite decay, including iron disulfide, which is right here, which often is a big component of a lot of marine fossils. So this is something known as an ammonite. And what happens when you have pyrites exposed to oxygen and water is that you can also, again, get sulfuric acid. And you can get some pretty funky things that happen to your poor ammonites. As you can see, like this is a kind of a mess right here. You get like these really weird little whiskering effects that form from the production of various salts as a result. But basically, this is a good way to lose your fossil collection. So again, even things we think of as being pretty impervious to time and most types of chemistry can have been affected by strong enough acids and bases in the right post-burial conditions. Then there's also, so that's sort of the sins of the past, the things these artifacts bring with them from the burial environment that we have to contend with. We also have to contend with our own sort of set of challenges in terms of our own materials that we use to house and store these artifacts. And a lot of this has to come down to a lot of the materials that we use, both in terms of our casing, tissue paper that we use to wrap things, boards that we use to support things and help section things off. Is that they contain something called hemicellulose, which hydrolyzes quite easily. This includes things like our hardwood, this includes MDF board, any types of pressed particle board, anything that's acid-free or not acid-free papers and things like that will contain a lot of hemicellulose that breaks down in the presence of water and oxygen and creates a bunch of what we call volatile organic compounds or VOCs. So these are things that are continually basically off-gassing or kind of seeping out of these elements over time in the right environmental conditions, including things like acetic acid and formic acid. A lot of pressed board also contains formaldehyde, which can very easily be broken down into formic acid as well. So what happens is that if you have your objects stored next to these materials, in these materials, if they're in like a nice oak hardwood case, for example, then you can get some really interesting acid-base reactions. A lot of times this acetic acid and formic acid will deposit on the surface of artifacts. So you have this basically basic acidic salts that are forming on the top of your artifacts that again can at any time solubilize and start attacking your artifact. This is particularly a problem with pewter and lead. You can see there's a particular type of lead attack that can be very devastating due to the presence of these acids. And it's one of the biggest reasons why we do not display or store lead with anything that is made of wood or wool, because wood and wool artifacts can also contribute acids of their own, as we've talked about, as they break down. So if they're in an environment, a shared environment with some of these more sensitive objects, they can lead to their hydrolysis or their dissolution. There's also atmospheric pollution, so things that are just produced by industry, by cars, by smokestacks, things that we put out into the environment as a byproduct of our own industry. These include things like nitrogen dioxide, sulfur dioxide, ozone, which can very easily become basically acid rain, essentially, or other types of acidic compounds that are in the environment. This often contributes to things like why silver tarnishes, even in a fairly stable environment. Can also do kinds of really nasty things to cloth and other types of textiles in the environment, even ones that we use in our as sort of display backing. And there's also finally our own conservation materials. A lot of these materials are adhesives that we use to, put things back together, to glue them together, that we use to consolidate with, can lead to, they decompose over time themselves. They are also on sort of their own aging trajectory. And over time, a lot of these materials, especially like PVAs, for example, will break down over time and become acidic. So they can actually introduce acids and bases into our artifacts vicinity. There's also a lot of types of polishes and cleaners and types of chemical reagents that we use to address either acid-based problems or other problems, or just to clean our artifacts that themselves are acidic or basic. And the problem there is when we don't rinse those artifacts sufficiently, when we don't remove that acid or base component that we've introduced sufficiently, and we leave it behind, it can cause problem down the road. And then there's also just handling. Our ability to touch and work with these artifacts can, as we sort of previously talked about, can leave acids on the surface that can affect them, etch them, introduce localized types of acid-base reactions to these artifacts. So how do we address these problems? Well, to address problems kind of with a post-burial phenomenon, to try to deal with the products that are left behind, we do several things. We neutralize and we alkalize, for example. This is an example of, I believe, some copper that has been removed from a saltwater marine environment, and we are trying to basically de-acidify it. And what we do is that we add in a base. We add in a solution, a base to our solution. A lot of times these are basic salts. They get put into a water bath, essentially, and they create a buffer, which means essentially that this is iron. You have your iron set up, you have that ferrous chloride breaking down and becoming hydrochloric acid. If you add a base to it, if you add a source of hydroxy, then all of a sudden that hydroxy can basically partner up with those hydrogen ions instead and create harmless water, essentially. And obviously, the more you add to it, the more alkaline this material becomes. And the more hydroxy you add to this, and this goes back to my comment earlier about the different pH of an environment influencing what types of corrosion products are produced, is that these hydroxy ions will then, there's enough of them, they're sort of the most common portion of the solution at this point, that our iron will then preferentially start forming types of salts called iron hydroxides, excuse me. Iron hydroxides are much more stable than any type of iron chloride product. And what happens is that this actually becomes sort of almost its own built-in buffer, because you all of a sudden you have this built-in source of hydroxy ions that are in this corrosion product. So what happens is you get sort of a passivating effect, where essentially if there's any future acid buildup that occurs, all of a sudden you have all this hydroxy sort of built in and being carried around by your actual artifact that can sort of respond to that, because that hydroxy will be available to interact with those hydrogen ions and sort of neutralize them or remove them from interacting with the iron. And so when it's metals, we call it passivation. When it's things like paper, we call it alkalinization. And this is an example of calcium hydroxide is often used to help with acidic papers, for example. Not only does it then neutralize the pH by sort of using up all those hydrogen, it also leaves a reservoir of calcium carbonate, which is the conjugate acid of calcium hydroxide, which can very easily become calcium hydroxide again if in the presence of acids. And creates this sort of really self-sustaining buffer reservoir that it creates in this paper. So basically trying to booster the alkalinity of a lot of types of artifacts and leave some source of alkalinity with them often helps in future acid attacks. Similar thing with our poor ammonite over here. The way we treat these is with ammonium hydroxide. This is an example. These two examples were actually kind of solution-based. It really involves immerging your artifact, usually in a water-based solution where you have a dissolved basic salt. Ammonium hydroxide, though, is actually a gaseous treatment. We basically create ammonia gas, which will then interact with our sulfuric acid and create a much more stable product that, again, has that sort of buffering effect. It is a conjugate acid that can kind of reverse itself and become a base when in need. So those are ways that we're able to neutralize both the activity that is currently happening and also sort of buffer against any future activity. And sometimes, so those really work with things that are soluble. And then, I'm sorry, okay. Going back one step, soluble salts again, the way we address soluble salts is called desalination. So basically it's a series of water baths where we essentially diffuse out some of those troublesome salts or troublesome components of ions that can become those salts that can deposit within the artifact later on and cause physical and chemical damage. We also remove them physically. Sometimes there's just too much buildup. Sometimes those salts are what we call insoluble. They are not readily soluble in water by themselves. In order to deal with those, a lot of times, or sometimes they're corrosion products that are just, they've migrated onto an object that they should not be on, and there's not enough, passive diffusion in water is not really going to get these off. So what we do is that we mechanically remove them using different types of tools. So dental tools, scalpels, brushes, different types of hand school tools. In instances where there's just too much of it, or it's too thin or too delicate for physical cleaning, we also do have chemical means of treating insoluble salts as well, or insoluble corrosion products that are kind of potential reservoirs for acid-base activity. And we use these kind of ironically. This includes silver sulfide, which is a very insoluble, very intractable material that forms on silver artifacts. A lot of carbonates that form on things that are made of lead or tin, for example, are very intractable. You also get carbonate salts on top of ceramics, for example, which basically will not dissolve in water. And as we talked about, we kind of use the acid-base chemistry against itself. So remember that acids and bases can change how soluble something is in water. And that's basically what we're doing here, is that we then actually will use oxalic, formic acid, other types of acids in a very controlled way and always with a buffer, in a way to basically increase the solubility of these very insoluble salts and are able to then sort of rinse them off or remove them using water after the fact. Some materials, if this is too rigorous to sort of outright expose them to an acid environment, we'll also use something called a chelator. A chelator is a special type of molecule called a ligand, which is able to bind to metal ions. So it basically binds to the metal parts of carbonates, or the sulfide part of sulfur, to be able to remove it from solution, and basically breaks that molecule apart and basically disrupts it on its own. Two examples are ammonium citrate and EDTA. These are chelators. I will eventually have a presentation going into more detail about chelators, so I'm not going to spend too much time on them. But these are chemical means that we can remove potential reservoirs of acids and bases, which we can't remove just by soaking them or mechanically. And of course, anything that we use that has a pH that is not neutral, any acid or base that we use, we also rinse everything really well to make sure that we're not leaving any residual acid or bases on the surface of the artifact, inside the artifact. This is a very important step. It's one of the reasons that certain processes sometimes take longer than we think they should. All right, and how do we then deal with acid-base problems once we've treated your artifact? Okay, you've treated your artifact, you've done everything you can to buffer it, to make sure it's as stable as it can be. You're going to put it in display, you're going to put it in storage. What are you going to do to make sure that the environment of your storage or your display area is not also going to become a reservoir and a source of acids or bases? Well, we replace a lot of our wooden cabinetry, a lot of things made with MDF board or things that are acidic, with glass and with acrylics, things that are very inert to themselves that aren't going to be off-gassing VOCs. If we do use wooden cases, which we still do, we tend to seal them or cover them with something that basically can block those vapors or absorb those vapors or neutralize them. There are special types of foils, there's special types of primers, and there's low VOC paints as well that either don't emit any of those materials or else they sort of insulate the material inside the case from the case materials, or sometimes they even absorb them, kind of scavenge them from the environment. We also, when we have artifacts, there are two different types of materials. They're an organic material and an inorganic material like lead and a piece of wood, for example. And we know that combination of them being physically in the same area is going to be a problem. We'll separate them in storage or we'll display them separately. And in instances where we do display them together, these kind of lead objects over here and this wood, or these pewter objects over on the right and this wooden head on the left, for example, if they're going to be displayed or stored in the same case, because that's just what's going to happen, then we do something called, we create a microenvironment where we might put basically a case within a case. We might put one or more of those objects in its own case within the case to try to protect it from that exposure to those volatile organic compounds. You'll actually see that in the gallery as you go through, especially some of our more archaeological sections, that if you're looking in the cases, you wonder, like, why is that spoon in its own box? That is one of the reasons we do it. It's probably, it's to kind of protect it from potential exposure to those organic acids that could be in the environment, either from the display cases themselves, from other artifacts, or from atmospheric pollution. Other things we do to try to control the environment and eliminate and reduce acid-base reactions is we try to control the humidity. So we try to eliminate a lot of that water, that universal solvent that's in the air, that's around to sort of, precipitate and dissolve salts. It's there to kind of kick off a lot of these acid-base reactions. As we said, water itself is both acidic and basic as well. So we try to remove as much moisture as we can from areas where artifacts are stored or displayed. This can be making microenvironments. This can be including desiccants like silica gel in cases. And this can be also for the use of dehumidifiers or really fancy HVAC systems that air condition the air, sometimes even in the cases directly. We'll also add in what are called scavengers. Tarnish strips, oxygen scavengers. These are things that either remove airborne atmospheric pollutants like sulfurs or oxygen from the environment, and also kind of basically eliminate those components that are needed for acid-base reactions to happen. And then we also coat things. It might be our furniture, our exhibit furniture, or might be the artifacts themselves. We often, especially things that are made of metal, we tend to apply special barrier coatings that protect them from oxygen and water and acid attacks as well. So they're not getting those VOC vapors in contact with them. And then finally, as conservators, we've developed products that are much more pH neutral. They are things that do not break down and create acids or bases, that will not change the chemistry of the artifacts they are applied to, at least not in any type of significant time frame. We also, again, take a lot of care to make sure anything we touch, anything that's in the lab, anything that's been treated by chemical means in particular, that is well rinsed, it is well swabbed, it is well basically surface cleaned, degreased, whatever you would want to term it, to make sure that we try to remove at least the superficial surface deposits that either we leave on the artifact through treating it or handling it, etc. And of course, we wear gloves. Number one reason why we wear gloves is not to protect ourselves from the artifacts. It is purely most of the time to protect the artifacts from ourselves and from our acids and body greases and oils. Thank you very much for your time. If anyone has any questions, please feel free to ask. Otherwise, please come back on October 6th at 11 a.m. for my colleague David Bennett's next talk in the Meritage Heritage series titled North Carolina's Mullet Fishery. And we are now open for questions. Anyone have any questions?
Does extreme temperatures affect?
That is a very good question. The question was, does temperature affect acids and bases? Does it basically affect how well or how much damage the acid is able to do? Is that, yes. Basically, what temperature is, temperature doesn't necessarily affect the chemistry. Temperature can speed up reactions essentially. So yes, if you heat something, you add more energy into the system. That influx of energy can make the reaction go faster. Whether or not it's an order of magnitude in terms of the actual damage it does is depends on the artifact, depends on sort of the acid that is being used. But yes, boiling acid is used. And it can, obviously, the being dissolved by a gaseous form of it versus a liquid form of it can change the chemistry a little bit as well. So I guess the answer is yes to a degree. So. Anyone else? Anyone online? All right, well, thank you very much, everyone, for your time. I'll hand it over to Ben. Do you want to check and see these? Well, thank you very much for coming to. Yes, if you have any feedback also, I've been trying to make this a better presentation, so. Anything, just in terms, anything that you felt needed more clarification, that could have used, was unclear, that was difficult to follow? Well, thank you so much for coming and sitting through. Well, thank you so much for coming and sitting through it. I appreciate it. So, but yes, this is chemistry taken from the abstract classroom and kind of see how it applies to real life things. And so. Yeah, it has its problems. So. Yeah, unfortunately, this was a kind of an example of aesthetic over functionality. So it looks beautiful, we love it, but yes, it does have the capacity to cause problems. So.